and then these projection type problems, and I asked you guys to work on 41 through 50 from the problem set. I'm going to start today by taking questions. You can go to the previous 1 through 40, or you can ask about things from 41 through 50. Either is okay. Mackenzie. Sure. So 47. Let's do this. I don't think I want to write all these words. So what do we got? We got a crate of negligible weight is being pulled up a ramp at an angle of elevation of 38 degrees with a force of 120 pounds. The ramp has an angle of elevation of 25 degrees. What amount of force is being directed up the ramp? So I'm going to start by just kind of drawing a picture. When I read this, Mackenzie, how many vectors do you hear? I hear 2. I hear 1 for the pull and 1 for the ramp itself. So let's see, the pull vector may be here. So I'm going to use P for that. So it's pretty easy to see that the magnitude for P is 120 pounds. And the direction for P is 38 degrees, since it's talking about an angle of elevation. And then we have our second vector is this ramp vector, which has an angle of elevation of 25 degrees. I'm going to call that vector R. Now, it should be easy to tell that the direction for vector R is also just going to be 25 degrees. But what's the magnitude for vector R? Yeah, it's not given 1, right? So what does that mean we can do? Yeah, we're going to choose it to just be 1. So not finding. We're just going to choose it to be 1. So I'm going to go ahead, now that I have my 2 vectors, what I'm going to be looking to do is I'm going to be making this projection vector from P onto R. And we're actually going to be looking for the magnitude of that vector. We okay with the picture that I've drawn in terms of what we're trying to do? Okie doke. First step is going to be to resolve my vector P and R into component form. So again, that's just magnitude times cosine of direction, and then magnitude times sine of direction. Cool with that? Oh my goodness. That should be a 25. Cool with that, Mackenzie? Okay. Now, since my vector I'm projecting onto is a unit vector, I can use that shortcut that we talked about last time. So the projection of P onto R is going to equal just the absolute value of the dot product of P and R, which is nice. That saves me a lot of work. So when I do that, I just get 120 cosine 38 times cosine 25 plus 120 sine 38 times sine 25. And it's calculator time. I get 116.92 pounds up the ramp. Does that feel okay, Mackenzie? Yep. Notice that I'm using this shortcut only because I'm projecting onto a unit vector. If you were not projecting onto a unit vector, that shortcut does not work. But it did this time, so that's nice. Who's up next? Jackson?
Number 49.
Okay. Somebody always asks about one of these last two because they're basically the same problem. All right, so 49 says a crate weighing 50, well, what is ibises? Just pounds is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. The ramp has an angle of elevation of 35 degrees, the amount of force being directed up the ramp. So when we read this, Jackson, how many vectors do you hear?
2.
That is the problem. There are 3 vectors in this problem. So you have a vector due to gravity acting on the crate because the crate has a weight. You have a vector pulling the ramp, so 48 degrees, or 48 degrees and 150 pounds. I call that vector P for pull. The previous vector I called G for gravity. And then lastly, we have our ramp vector. And again, the direction there is 35. We're not given any idea of the length of the ramp, so we're just going to, again, choose it to be a unit vector, make it equal to 1. So far, so good? Okay. Now, in this problem, both gravity and the pull are interacting with the ramp, are putting force into the ramp. So we have 2 options here as to what to do. We can kind of use our picture and look intuitively at how to do that, each of the projections separately, and then determine whether we should be adding or subtracting them. Or what I would prefer is I'm just going to add the vectors P and G together and then project that resultant onto the ramp, which I think is the easiest way to do this, since adding vectors is not a problem. So again, I'm going to just skip the formulas on some of these and just now write what the values are, if that's cool. So I got 100.37 and 111.30 or 47. I have 8, 20, and 57. So far, so good. Okay. So P plus G, I guess I could have written that as G plus P. It doesn't really matter. Adding the two vectors, that's easy to do since the numbers are really convenient. And now what I want is the magnitude of the projection of P plus G onto R. Now this actually turns out to be easy again because R is a unit vector. I can just do it as a dot product, or the absolute value of a dot product, but pretty obvious to know that I don't really need the absolute value because since all the components are positive here, you know. So what do I get? I get 100.37 times 0.82 plus 61.47 times 0.57. Let's see, so I need this one times this one plus this one minus 50. I'm going to stick that in parentheses rather than doing the 61 in there, times this stuff. And I get 117.47. Up the ramp. So not really any harder than the previous problem, but you had to recognize that you had three vectors there going on. What's up? Oh, okay. You just had to recognize there are three vectors going on, and then to add the two that are interacting with the ramp vector, and then do your projection, which again wasn't too bad, especially since the ramp vector was a unit vector. Made life easy because we could take that shortcut. I think 50 is the same setup, basically. Every year, everybody asks about 49 and 50 on this, so like, was expecting it. At least if you'd gotten there, you'd have been like, what? I can't get the right answer for 49. I'm not going to try 50 yet, which is what I'd expect. Now the tricky part is if you didn't try to do it as a vector sum, you'd have to intuit that like gravity is going to be pulling the crate down the ramp and the pull is going to be pulling it up the ramp. So when you find the force of the projections of each of them, you have to subtract the gravity from the pull. So those two projections get subtracted, which is not obvious until you like really think about the physics of it, which I'm not keen on. I'd rather just let the numbers handle the whole thing, which is why I prefer to just send them both to vectors, add the two vectors, and then project the resultant. which I think is the more straightforward way of doing it. But you could have also done it that way if you had tried to get it to work that way and you got it to work. That's not incorrect. But that's something that I would end up screwing up, is like, oh, should I be adding or subtracting these two forces now at the end after I do my projections? That seems like a Mr. Kulik mistake. You don't have to worry about that, though, if you just add the vectors. Anybody else?
I have a
Paul?
question on that. So, when you were saying you subtract the gravity by P, G by P, you would only subtract because a force pushed down.
Well, if I put a crate on a ramp,
Right.
and I don't interact anything else with it, it's going to slide down, right? It's going to be moving down the ramp. So the projection of gravity onto the ramp is going to be like a negative force.
Oh, okay.
And the projection of the pull that you're pulling up the ramp, the crate should be moving up.
Pulling up.
So that force should be positive. When you do the magnitude of the projections, they're going to both give you positive numbers, but you have to end up subtracting them, which is like the not obvious part.
Gotcha. So if it was anywhere in the third or fourth quadrant, if gravity was for some reason anywhere in the third or fourth quadrant.
Well, gravity's always going to be pulling down.
Right, but like
If you had a force
that was in that
in
direction, then you subtract.
Ooh, well, not necessarily. Because if you had like, a force like this,
Right.
I think that's still going to be moving up the hill net, because most of that projection is going to be going to the right. So you're going to have a lot of it going. There's very little kind of pulling down,
Okay.
because the y component of that's pretty small compared to its x component that's really positive. So it's hard to say. It's not as simple as just what you want to say,
Yeah.
which is why adding the vectors makes it way
It
easier.
would make a difference because of the
Yeah,
situation.
yeah.
Yeah.
So I don't want to say like as a hard and fast rule like that, because I don't think I can. I think you could create a situation where you have a vector in the fourth quadrant that's still kind of heading up the ramp.
That's what I was wondering.
I'm not positive, but I'd be real dubious, and I don't want to commit to that at all without like really thoroughly thinking about it. Okay. All right. Last call here. No worries if you want to come back at a later date and ask more. But if there's nobody else for today, let's go ahead and move on and start talking about our next stuffs. Okay, seems good. Nobody's barking at me, so. Our next section here is called 2D Vectors in Space. Right? It sounds like a cartoon title or something. No? I think it does.
I think
It's not a 3D graph stuff.
We'll get to 3D stuff later on this chapter still. Yeah, that's right. Big woof on that one. We're going to start here and introduce another vector notation. And you got to be going at this point like, woof, Mr. Kulik. This vector notation we're going to call IB component form. But you'll have to excuse me. In my education, we just called this like a column vector, and I'll probably end up using that vocabulary a lot because was drilled into me pretty good from way back in the day. Even though our textbook is calling it this IB component form or whatever. So if we have a component form vector, looks like this. Our IB component form we're just going to write as AB as a column. Notice that there's not a bar in between the A and the B. It's not a fraction that we're writing. it's like a 2x1 matrix. That's 2 rows and 1 column. But we're going to use the parentheses as opposed to a bracket. You might see this referred to as a column vector or a column matrix. But that's an easy switch to make, right? Like there's ain't nothing to that one. Other than remembering the name, and at this point you got to be like, yo, Mr. Kulik, we have like 6 different forms that we can write a vector in. This is getting a little ridiculous. And I was like, well, that's one of the things that's hard about this chapter, is just keeping all the names straight, because there's a lot of them. Okay. One of the main goals that we're going to have today is we want to create a way to express the equation of a line as a vector, using vectors. So what we're going to start doing is creating a vector line equation. So let's just kind of take an example, and we'll use this example to kind of generate the idea here. So let's just say we have the line y equals 1/2 x plus 1. Pretty straightforward. You know, you'd have a line that looks like this, right? Slope's positive, so the line's going up. The slope's only 1/2, so it's not going up very steep. And the y-intercept is there about 1, 0, or 0, 1, excuse me. Everybody cool with that? Seem reasonable to you guys? Okay. So one of the things that I can do with this line now is this line contains infinitely many points, right? So I could really kind of pick any point on this line by just picking a value for x and finding the value for y. So for example, like 2, 2 would be a point on this line. Right, if I plug in 2 for x, I get 2 for y. You guys agree with that? Yep. Okay. If I use that, then I can find a vector that's in the same direction as my line, either going that way, or I could, find a vector going the opposite way. So that's kind of what we're going to be looking to do, is just create a vector whose initial point is some point on the line, and the direction for that vector is the same direction as our line. Okay with that? So to express this vector here, we're going to need a magnitude and a direction for that vector, correct? So let's do the direction piece first. What attribute of a line do you suppose is going to serve as our proxy for direction? So what attribute for our line is going to basically give us the same information as its direction? There's only a couple of things you can guess, because line only has so many attributes, right?
Positive or negative?
No. What's one way that you can describe a line? Slope. The slope is going to serve as our proxy for direction. In this graph, or this line, what is the slope? What is the value of the slope in this one?
1. Half.
1/2. Okay. And when we calculate slope, how do we do that?
Big X minus y1 minus y2 over x2 minus x1. Other way around. I don't know.
Well, you had your 1s and 2s all screwed up there, but
Okay.
so the change in y over the change in x, right? Everybody's good with that? Now our direction vector, I'm going to abbreviate that with the letter V, is going to be 2, 1. Why is that? Because the x part of our slope is 2, and the y part of our slope is 1. Everybody okay with that? Now, if I have a starting point on my line that's represented by some point, and I'm going to just be a little bit more arbitrary here and call this point P naught. That's a P with a little 0 as the subscript, instead of a specific number like 2, 2. But any point on the line is fine. It doesn't have to be 2, 2 or anything. It just... Okay, so we have a starting point and we have a position vector, or direction vector, excuse me. So we can say then, oh, okay, well then like, we'll just write something like this. The line is equal to the point P naught plus the vector V. Woof, that's wickedly wrong. What's so wrong with what I've written there?
Because you're adding stuff with vectors. It's not a vector.
Yeah, I'm adding a point to a vector. Well, I can't do that.
Yikes.
And then when I get that, that's somehow supposed to equal like, still equal a y, which is like what? Like an equation for a line? I don't know. Like, that's bonkers.
Multiplying potatoes and carrots.
Yeah, so that doesn't make sense. So rather than using a point P, we're just going to use the point vector P. And the point vector P is just like, you know, would be like this, right? Starting at the origin and just going to that point P.
Wait, so it's always very important.
Yeah, so the component form is just like, if the point's 3, 5, then we're talking about the vector 3, 5.
Yeah.
So just as an easy one-to-one. Everybody's okay with that notion? Now there's, yes, sir.
And for the direction vector, so 2 is in triangle X.
I'm sorry, what?
I'm just trying to make sense of the placement of like the numbers in the direction vector.
Okay.
So I assume 2 is on top because that's where the direction is primarily headed. It's
Nope.
arrow.
Nope, it's because the slope formula is change in y over change in x, and we write our column vector as the x component on top and the y component on bottom. So it just has to do, it's just that way because the x part is on top and the y part is on bottom. That's all. Is that okay?
Yeah.
So if we do this, if we call this, okay, well, then we'll just say the vector y is equal to the point vector plus the direction vector. Then that's it, right? No, not quite. Because really, we should be able to generate any point vector that lies on this line. So like I would want to be able to say, okay, you know, this point vector, but P naught is a constant and V is a constant. And if I add these two constants, I can't get any point vector on the line. So that's not kind of a problem, right? Everybody kind of see that issue? So here's the fix, and the fix is quite easy. I'm just going to add on a parameter t. T is just a scalar that we're going to multiply v by.
Are you allowed to?
Well, if I do scalar multiplication, that doesn't change the direction of the vector. So the direction vector stays intact, and now it can become as long as it needs to, so I can cover any point vector on our line.
And it's different because t isn't a number, it's more like a measurement thing.
Well, t is just some real number, but it's like a variable. It can be any real number you want.
Right.
So you can generate any point vector then that lies on that line.
So you're just expanding, really. It's just not.
Yeah.
It's like changing from a teaspoon to a cup.
It's just
It's an
scaling.
infinite cup.
Yeah, yeah. Okay, oops. But this is not the letters that we use to represent our formula. The tradition is to use R, R naught, and then VT. Okay, everybody okay to hear? You ready to do some like number specific things so we can get a handle on how this is working? That feels like it's probably at that point. So let's do a couple here. So let's say we want to find a possible vector line equation for y equals 3x plus 5. So all I need to do here is I need to get a point from that line. What's an example of a point from that line?
1, 2, 2.
No.
No, that's not right.
I mean, why not just do 0, 5, guy, right? Like, use the y-intercept. It's the easiest one to get. So I can change that into the point vector, R naught, which is the point vector 0, 5. Oops. We good there? Then I'm going to need the slope from our line. What's the slope from our line? Anybody? 3. I'm going to write it as 3 over 1 because I want to change that into a direction vector. What would the direction vector here be?
1, 3.
Good. Everybody happy with what we did? Very easy, right? So all I have left to do then is to put it together. You feel okay with that? What if I asked you to write this in linear combination form? Who remembers what linear combination form is? It's the one with the I and the j vectors in it. Does that ring a bell? So I'm just going to change my vectors into that linear combination form. Everybody's okay with that? All I did is take the x's and slap an I on the end of them, and the y's and slap a j on the end. Tegan? Sure. Yeah, no problem. And now all I'm going to do is I'm going to distribute the t through and then regroup the i's and j's together. Call that ti.
Is that one I?
Yeah.
Why is it one I? Oh, never mind.
Because that was the vector 1, 3. So again, that's representing the same information as the previous one. It just, we wrote our answer in a different form. Is that okay? Just to kind of practice changing forms again between vectors. The directions of the problem didn't ask you to do that, but I think in the homework set, one of the problems asks you to write the equations in linear combination form. So probably not a bad idea to just squeeze that as an example in. Somebody asked about that during second period after the end. I'm like, should have done that. So we did. Okay. Let's do another example. So here we're going the reverse direction. We're going to take our vector line equation and put it into slope-intercept form. To write an equation for a line in slope-intercept form, you need two pieces of information, right? You need either a point and a slope or 2 points, correct? You can get either set of information from our vector line equation, although I think the easiest thing to do is just go with the point and the slope. So your point vector will just turn into the point 3, -1. Our direction vector, 2, 3, turns into the slope, 3/2. And now it's like a pre-algebra problem. So we just plug in our point and our slope, and we solve for our y-intercept. So 3/2 times 3 is 9/2. When I subtract that from both sides, I get 11/2 for b. So y equals 3/2x minus 11/2. Taylor, question reading my chicken scratches?
Well, just a little bit.
Okay. If you need to turn the lights out, that sometimes helps make everything a little bit sharper. You're welcome to do that if you'd like, if it makes life easier. Really, at any point during any time, if you feel like it's easier to see the projection with the lights out, you can just stand up and turn the lights out. You're all welcome to do that. I would not be offended at all. Plus, I look better when it's dark. That's a joke about just like being ugly in general. We're all pretty with the lights off. That's the biggest laugh I think I've gotten out of anybody all year there, Emma. So I don't know what to think about that. All right.
Such a comedic career.
Yeah. We'll do one more example here, and this is the most in-depth one. So here we're asking to find the intersection between the two lines. Now, I want to say for a minute, there's nothing wrong with taking each of these lines and turning them into slope-intercept equations and then solving them as you would in your Algebra 2 class. However, doing this the vector way, which we're about to show you, becomes useful and becomes part of future routines. So even though it's okay to write these as slope-intercept equations and then solve them like we would in Algebra 2, I'd encourage you not to do that here because this becomes a useful technique as we move forward in this chapter and then in future chapters. So I would advise you to do this the way that I'm about to show you, just for practice's sake. Is that okay? Again, nothing wrong with doing it as just turn these into slope-intercept equations and solve. Just, it doesn't help us out in the future very much. Okay. So a lot of the same intuition that we used when we solved a system is going to be the same intuition at play in here. So if I want the intersection of these two lines, I need a point vector that I can generate with R1 and a point vector I can generate with R2. So what I'm going to do is I'm going to think about R1 as the point vector xy. And I'm going to do the same thing for R2. So what I'm going to do here is I'm going to do my scalar multiplication and vector addition for each of these. So that's going to be 2 plus 1s, and then 4 plus 3s, and then negative 1 plus 3t, and then 5 plus 5t. Everybody okay with how I did that? Again, pretty simple. What I'm going to notice here is that x has to equal 2 plus 1s, And x also has to equal -1 plus 3t. So I can say 2 plus 1s has to equal -1 plus 3t. And then similarly, y, I can do the same thing. And if this is, and I need these x's and y's to be equal at the same time, so they need to be happening simultaneously. So I really need to think about this as a system of two equations. Is everybody okay with how I generated this system? Okay. So I'm going to now take a moment and rearrange my system so that it's in kind of that standard linear form. So to do that, in the first equation, I'm going to subtract 3t from both sides, and then subtract 2 from both sides. And then similarly, in the second equation, I'm going to subtract 5t from both sides and subtract 4 from both sides. Everybody's okay with that? So what I have here is a system of two equations. If you think back to your Algebra 2 class or equivalent, what was the fastest and easiest method we discussed to solve a system of equations? Particularly if you had Mr. Kulik's class. No, I would not say substitution.
Subtraction.
Not elimination. There's a faster and easier method than either of those two. Definitely not mental math. I would use a matrix and use row-reduced echelon form to solve this, since that can be done entirely on my calculator. So to review how to do this, I'm going to start by opening my matrix menu by pressing second and the x to the -1 button. To enter a matrix into my calculator, I'm going to go over to the Edit tab and pick a matrix. The matrix that I'm going to be building needs to have one row for each equation, so that's 2 rows. And that needs one column for the s's, one column for the t's, and one column for the answers. So that would be 3 columns. So I need to build a 2x3 matrix. And the matrix that I build here is just going to have entries that are the same as the coefficients. So 1, -3, -3 is my first row, and then 3, -5, and then +1 is my second row. Everybody feel good there? Once I've entered in my matrix, I'm going to exit back out to the main screen and then go back into my matrix menu. This time I'm going to go to the Math tab. And from the Math tab, I'm going to go ahead and select the command RREF near the bottom. That stands for row-reduced echelon form. Make sure you pick RREF and not REF. There is a big difference. And I'm going to do RREF on that matrix B that I just created. So I'll go back to the matrix menu. From the Names tab, select matrix B.
That's reduced row echelon form.
Row reduced echelon form, yes. And there's my answer. If I'd prefer fractions, I can do the math fraction command on that matrix, and it'll give me it in fractions also. If the decimals were particularly yucky, that might be a better option. Okay, so let's just kind of sketch some notes about what we did. So we did RREF on the matrix here, which output 1, 0, 9 over 2, 0, 1, 5 over 2. So somehow now this matrix that I have, 1, 0, 9 over 2, 0, 1, 5 over 2, is going to tell me the values for S and T. If I go back to my original matrix, I put the S's in the first column and the T's in the second column. So what this first row says is that 1S plus 0T is equal to 9 over 2, or that just S is equal to 9 over 2. The second row says 0S plus 1T is equal to 5 over 2, or rather just that T is equal to 5 over 2. So far, so good? Repeat what again? So if you read the first row, that's equivalent to the equation 1S plus 0T is equal to 9 over 2. Or just S equals 9 over 2.
Oh, I see now.
And same thing on the second row.
Okay.
Because that's the form that we put in, put our stuff into our calculator. Okay. And just as an aside here, you have to have a system that looks like this to use RREF. So you have to have it like the variables all lining up, the equal sign all lining up, the solutions all lining up.
What's REF?
It does it without making the coefficients on the S and T's 1.
So we won't use that.
We will not use it in this class. Okay, so we're almost done here. So now we need to pick either S or T, it doesn't matter. Just pick one of them. I'm going to pick S. So once I have S, what I'm going to do is I'm going to take my vector line equation that had the S in it, and plug in 9 over 2 for S. So when I do that, I do the scalar multiplication between the vector 1, 3 and the number 9 over 2. That gives me 9 over 2, 27 over 2 as my vector. And if I add the vector 2, 4 with the vector 9 over 2, 27 over 2, and make common denominators, I get the vector 13 over 2. Did I pick the right one here? Hold on 1 second. Yeah, that's my one with the S in it. Okay. 7 over 2. 2, 4. Okay. Okay. So what's that? 13 over 2. And then 35 over 2. That's my point vector. which just becomes the point 13 over 2, 35 over 2.
It's not a point on a vector anymore.
What's up?
It's not a point on a vector anymore.
So I transform the point vector into a point.
It's like you made Pinocchio into a real boy.
Yeah, that's exactly it. That makes me Geppetto. Or the wishing star.
That was pretty cool.
Yeah, for sure. So, wanting to make a point here. Remember how I said that in the beginning you could just turn these into slope-intercept equations and do it the algebra 2 way? Why am I asking to avoid that?
Because we're going to use this more.
If you get into 3 dimensions,
Okay, so
the direction vector no longer resembles a slope. No longer easy to do this. Now it becomes really difficult to transform these into 3 linear equations, and then to do the algebra 3 solve on it is a hassle. Much easier to go this route because it's really the same process. You just have a third component, a third variable in your system to solve for, but it's not a big deal because you're still going to use your calculator to solve the system. The system part is easy because of the way we're using our calculator to do it. That'll happen towards the end of this chapter. We'll look at 3-dimensional stuff. And then we'll see this process come up again when we talk about parametric and polar equations later on this semester. We'll see this process come up again. We can use it there as well. Any questions about what we did here? Do you want to walk through this process one last time? Just to see the overview here?
yes.
Okay. So what we did is we said, okay, we're looking for the point vector in common between both of lines. So we represented those point vectors as x, y. We described x in terms of R1, x in terms of R2, y in terms of R1, y in terms of R2, and then set the x's equal to each other and the y's equal to each other.
So we basically just kind of spell that out.
Yeah. We then rearranged our system to get into a place where we can do RREF on it. We solved that system using RREF to get the values for S and T when the intersection occurs. And then pick one of the 2 variables and plug it into the correct or to the corresponding vector line equation. That gives us the point vector at the intersection, which we just converted into a point.
Go back to the top.
Sure.
So you always convert things into points between the covering points.
All I did was add vectors and scalar multiply to do that very first step. Or scalar multiplied and then added vectors, I guess I should say.
If I wanted to put 2 over 4 in parentheses into a point, it would just be 2, 4.
Well, it's not 2 over 4.
Okay.
It's the vector 2, 4.
Okay, so if I wanted
Becomes the point 2, 4.
okay, so if I wanted to put vector 2, 4, I would put it would be 2, comma 4 as a point.
Yes.
Okay.
Nothing sneaky about converting from a point vector to a point.
Okay.
It just
Either vector.
all you do is just write it horizontally,
I see.
or vice versa.
Just so I understand, the vector is just going to be the line across.
Pardon?
So the vector is going to cross that point then?
The 2 vectors intersect at that point that we found. Yes. Okay. This feels like a good place to stop.
Yes.
At this stage of the game, you guys should be able to do up through 76. Notice that this part of the problems are not going on to this week's problem set, but rather next week's problem set, as you can see on the board. So for Sunday, you're going through 50. Next week, we're going to do 51 through 76 and a little bit more. I think last time I warned you about homework quiz coming here in the next couple of classes. If we didn't do it today, do you think the odds went up or down that we're going to do it the next class? At this point, Mackenzie, I would feel it would be fair to ask on sections 1, 2, and 3, since we've had a chance to talk about all 3 of those. Today we did 8-4, which I would not consider fair game for a homework quiz next class. Does that feel okay? And I would say that short of the projection equation or angle between two vectors equation, anything else I think is probably on you guys. So remembering the different forms and like how to convert between the forms, or like the magnitude, how to find a magnitude or how to find a direction. These things I think are, you're on your own for those equations. Or the basic vector operation equations like addition, subtraction, scalar multiplication, dot product. You guys should be able to do those without formulas. But the more complicated stuff like the angle between two vectors or the vector projection, I think I would probably give that to you. Okay. Any final questions for me?